Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore some fundamental concepts in data communication. On this first slide, you can see the key topics we'll be covering: datagram, fragmentation, options, and checksum. Over the course of this presentation, we'll dive into what each of these terms means and how they fit into the larger picture of network data transfer. Let's get started. Welcome to this introduction, where we'll explore some fundamental concepts in networking. We'll start with datagram, which is essentially the basic unit of data transfer in a network. Understanding how datagrams work is crucial because they carry the data across different networks. Next, we'll look at fragmentation. This is the process that allows large datagrams to be broken down into smaller pieces so they can pass through networks with size restrictions. Fragmentation is key to ensuring data reaches its destination intact, even if it has to travel through various network segments. Then, we'll touch on options, which are additional settings or instructions that can be included within a datagram to inform how it should be handled or processed by network devices. These options provide flexibility and control over data transmission. Finally, we'll discuss checksum, a vital component for maintaining data integrity. The checksum helps detect errors that might occur during transmission, ensuring the data received is the same as what was sent. Connecting all these points, this slide sets the foundation for understanding how data moves efficiently and reliably across networks. These concepts are essential for grasping the overall theme of network communication and data management. A datagram is essentially the fundamental building block of data transmission in a connectionless network, such as the Internet. Think of it as a self-contained, independent packet of information that travels across the network. What's important here is that each datagram carries everything needed for it to reach its destination, including both the actual data and the addressing details. This means that unlike connection-oriented communication, where a connection is maintained, datagrams are sent without establishing a dedicated path. They're crucial because they make networks flexible and scalable, allowing data to be sent efficiently even if some packets take different routes. Understanding datagrams helps us grasp how the Internet manages to handle millions of data exchanges smoothly and reliably. Let's talk about the features of datagram networks, starting with the size of an IP4 datagram. It can be as large as 65,535 bytes, which is quite substantial. However, not all networks can support packets this large because of their MTU, or maximum transmission unit. The MTU essentially defines the largest packet size that a network can handle without needing special processing. Now, when a datagram exceeds this size, fragmentation comes into play. Fragmentation is the process of splitting a large datagram into smaller fragments that are more manageable for the network. Each of these fragments gets its own header, which contains all the necessary information to reassemble the original datagram at the destination. Fragmentation can happen in different places, either at the source device before the datagram is sent out or along the route, by the routers that handle the packet as it travels through the network. This flexibility helps ensure that data can traverse networks with varying MTU sizes efficiently. Understanding fragmentation is crucial because it highlights how datagram networks maintain reliability and efficiency, especially when dealing with different network capabilities. It's a key feature that enables the seamless delivery of data across diverse network environments. A datagram, as we've discussed earlier, can be fragmented multiple times if necessary to fit the constraints of the network. This means that when a large packet needs to be sent, it doesn't have to wait or be blocked. Instead, it can be broken into smaller pieces. Now, an important point to remember is that each of these fragments travels separately. They don't stick together or follow the same path through the network. In fact, they can take different routes, possibly even arriving at the destination at different times. And here's something crucial to keep in mind. The reassembly of these fragments only happens at the destination. The network itself doesn't combine the fragments, it simply delivers them. Once all the pieces arrive, the receiving device reassembles the original datagram from these fragments. This process is vital because it ensures data integrity and proper delivery, even when fragments travel separately across complex network paths. So, in the context of our overall theme, understanding this fragmentation and reassembly process highlights how flexible and robust our network protocols are, allowing data to be reliably transmitted across diverse and dynamic network environments. Let's take a closer look at routing within a datagram network. In these packet switching networks, data is sent in the form of datagrams. These datagrams are essentially data packets that carry enough header information to be individually routed through the network. This means that each datagram knows how to find its way to the destination independently, without relying on a dedicated path. All the intermediate switching devices, like routers, use this header information to make real-time decisions about where to send each datagram next. This process allows for a flexible and efficient way to deliver data, especially in dynamic or complex network environments. These networks are called datagram networks because the communication relies on these individual datagrams, rather than establishing a fixed connection beforehand. This concept is key to understanding how modern, scalable networks operate. By routing each packet independently, they can handle a variety of traffic patterns and network conditions seamlessly. Let's talk about the routing principle in datagram networks. In these networks, each data packet is routed independently from the source to the destination, even if they are part of the same message. This means that each packet can take a different path through the network. Importantly, there is no prior reservation of resources or dedicated channels for these individual packets. Because of this, no fixed path is established beforehand for the entire message. Instead, each datagram is treated as an independent unit. Routers along the way use dynamically changing routing tables to decide the best path at that moment. This approach provides flexibility and efficiency, especially in networks with variable traffic conditions. It also aligns with the overall theme of dynamic and adaptive data transfer methods in modern networking. So, what this means is that two successive packets coming from the same source might actually take completely different routes to reach their destination. This highlights the dynamic nature of routing in networks, where paths can vary from packet to packet. Resources in the network are allocated on demand, following a first-come, first-served basis. That means the first packet that arrives gets priority for processing. When a packet reaches a router, it has to wait if there are already other packets being processed. This waiting happens regardless of where the packet is coming from or where it's going. This point emphasizes the importance of understanding how routers handle multiple packets simultaneously and how queuing impacts network performance. All of these aspects are crucial because they directly affect data transmission efficiency and overall network behavior. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the IP4 datagram header. This is a fundamental part of how data is transmitted over networks. The header contains all the essential information needed for delivering the packet correctly. It includes key fields like the source and destination IP addresses, which are crucial for routing the data to the right places. You'll also notice fields such as the version, which indicates that this is an IP4 packet, and the header length, which tells us how long the header is. Then there's the total length, which specifies the size of the entire datagram, header plus data. Another important aspect is the identification, flags, and fragment offset, which help manage packet fragmentation, especially when data needs to be split across different networks. The time to live, or TTL, field determines how many hops the packet can make before being discarded, preventing it from circulating forever. The protocol field indicates what type of data is being carried, like TCP or UDP, and the header checksum provides error checking to ensure data integrity. Lastly, the source and destination IP addresses are vital. They tell us where the packet is coming from and where it's headed. Understanding these header components is key to grasping how IP networking works and ensuring data reaches its destination efficiently and accurately. This header structure underpins the entire IP communication process, tying into the bigger picture of network connectivity. This slide doesn't contain enough information. That's why we're moving to the next slide. Now let's take a closer look at some key fields in the IP header. First, we have the version field, which is 4 bits long. For IP4, this value is always 4. It essentially tells us which version of the protocol we're dealing with. Next is the HLEN, or header length. This is also 4 bits and indicates how many 32-bit words make up the header. The minimum value here is 5, meaning 20 bytes, and the maximum is 15 or 60 bytes. This allows for optional fields if needed. Moving on, we have the type of service field, which is 8 bits. This is used to specify preferences like low delay, high throughput, or reliability, helping routers prioritize traffic based on the needs of the data. Then there's the total length, also 16 bits, which combines the header and data. This value ranges from a minimum of 20 bytes up to 65,535 bytes, defining the entire packet size. Finally, there's the identification field, which is 16 bits. This unique packet ID helps in reassembling fragmented packets, ensuring that all pieces of a datagram are correctly identified and put back together. Understanding these fields is essential because they form the foundation for how IP packets are constructed, routed, and reassembled across networks. They're the building blocks that enable reliable data communication in IP networking. Let's start by looking at the flags. There are 3 flags, each of which is just 1 bit. The first is the reserved bit, and it's important to remember that this must always be 0. Then we have the do not fragment flag, which tells routers whether they are allowed to break the packet into smaller pieces. The third is the more fragments flag, indicating if there are additional fragments that follow this one. The order of these flags is quite significant because they work together to control how data is broken up and reassembled. Next, we have the fragment offset. This is a key concept because it tells us how far along this particular fragment is within the original datagram. Essentially, it indicates the number of data bytes ahead of the current fragment. But it's important to note that this offset is specified in units of 8 bytes, not just individual bytes. This means that the maximum value for the fragment offset is 65,528 bytes, which is quite substantial. It helps ensure that fragments can be correctly reassembled at the destination, maintaining the integrity of the original data. Finally, let's talk about the time to live, or TTL. This is an 8-bit field, and its purpose is to prevent packets from looping endlessly through the network. Each time a packet passes through a router, the TTL decreases by 1. When it reaches 0, the packet is discarded. This mechanism is crucial because it helps avoid network congestion and ensures that data doesn't get stuck circulating forever. Overall, the TTL acts as a safeguard to keep our networks running smoothly and efficiently. Connecting all these points to the bigger picture, understanding these flags, fragment offset, and TTL helps us grasp how IP packets are managed and transmitted securely across complex networks. These features work together to ensure data integrity, efficient routing, and network stability. Now let's take a closer look at some of the key fields in the datagram header. First, we have the protocol. This is an 8-bit field that specifies the name of the protocol to which the data is being passed. Think of it as a label that tells the network what type of data it's handling, whether it's TCP, UDP, or another protocol. Next, there's the header checksum, which is 16 bits. This is really important because it helps us verify that the header hasn't been corrupted during transmission. It acts like a quality check, ensuring the integrity of the header information. Then we have the source IP address, which is 32 bits long. This is the address of the sender, the device that originally sent the data. Correspondingly, the destination IP address is also 32 bits and indicates where the data is headed, the receiver's address. Finally, there's the option field. This one is optional but quite useful. It can include additional information like source routing or record routing. Network administrators often use this to troubleshoot or verify whether a specific path through the network is functioning correctly. Connecting this all back to our overall theme, these fields are fundamental for making sure data reaches the right destination, intact and correctly formatted. They form the backbone of reliable data transmission across networks. Now, let's take a closer look at the options field in the IP4 header. All IP datagrams, regardless of their purpose, must include this standard 20-byte header. This header is like the datagram's blueprint, containing essential information such as the source and destination addresses, fragmentation control parameters, and length details. These are the core elements that ensure the datagram reaches the right place and is properly handled along the way. But what's really interesting is that, in addition to these fixed fields, IP4 was designed with flexibility in mind. The creators included the ability to add options. These are extra fields that can be used to modify or extend the way IP handles datagrams. Think of them as optional tools that can provide additional control, security, or functionality depending on specific network needs. This flexibility is a key part of IP4's design, allowing it to adapt to various requirements and future needs. It also helps us understand why IP4 has been such a robust and versatile protocol over the years, capable of handling a wide range of networking scenarios. So, the options field might seem like a small detail, but it actually plays a big role in the overall flexibility and effectiveness of IP networking. The IP datagram can include 0, 1, or even multiple options, which means that the length of the options field in the IP4 header isn't fixed. It varies. Now, each of these options can be just a single byte long, or they might be longer, spanning several bytes depending on how much information they need to carry. When there are multiple options, they are simply concatenated together and packed into the options field as a whole. It's also important to note that not all datagrams will have this field at all. In fact, the options field is optional, so if no additional options are needed, it can be omitted entirely. This flexibility allows IP4 to support a variety of features and extensions without making the header unnecessarily bulky. Understanding this helps us see how IP4 can be both efficient and adaptable, depending on the specific requirements of the network communication. What is fragmentation? Well, in simple terms, it refers to the way data gets broken into smaller pieces or segments. These pieces can end up scattered across different locations on storage devices. This scattering can slow down processes because the system has to search for and piece everything back together when accessing data. Fragmentation is a common issue in many storage systems, especially as data is created, modified, and deleted over time. It's important to understand this because it directly impacts performance. The more fragmented your data, the harder your system has to work to retrieve information efficiently. Addressing fragmentation is a key part of optimizing overall system performance. So, in the broader context of what we're discussing today, recognizing and managing fragmentation helps ensure faster data access, smoother operations, and better resource utilization. Now, let's talk about how data moves through computer networks. In these networks, data isn't sent as a big chunk all at once. Instead, it's broken down into small units called packets or datagrams. This makes it easier to manage and transmit across different parts of the network. However, sometimes these datagrams can be quite large, larger than what some networks can handle. Many networks have a maximum size limit for the data they can pass through at once. When a datagram exceeds this limit, it can't go through in one piece. That's where the concept of fragmentation comes into play. Fragmentation is simply the process of breaking a large datagram into smaller, more manageable pieces. Each of these smaller parts can then travel through the network without any issues. Once they reach their destination, these fragments are reassembled back into the original datagram. Understanding fragmentation is key because it helps us see how data can be efficiently transmitted even when network constraints are in place. It's a good example of how the network manages to handle large amounts of data seamlessly, maintaining reliable communication across different systems. Let's take a closer look at IP4 datagrams. They can be as large as 65,535 bytes, which is quite substantial. However, not all networks support such large packets because of their MTU, or maximum transmission unit, which is the largest size a network can handle in a single packet. When a datagram exceeds this size, it needs to be broken down into smaller pieces, a process called fragmentation. Fragmentation involves splitting the large datagram into smaller fragments that are easier to transmit across various networks. Each of these fragments carries its own header, which contains all the necessary information for reassembly later. This process can occur either at the source before sending or by intermediate routers along the path, depending on the network setup. It's also important to note that a single datagram might be fragmented multiple times if it needs to pass through networks with even smaller MTUs. Once all these fragments are in transit, they travel separately, often taking different paths to reach the destination. And here's a crucial point. Reassembly of these fragments only happens at the destination. The receiving device gathers all the fragments and reconstructs the original datagram before passing it on for further processing. Understanding fragmentation helps us appreciate how IPv4 networks manage to transfer large amounts of data efficiently across diverse and sometimes incompatible network environments. When a large datagram is created by the source computer, it might need to travel across multiple networks to reach its destination. And here's the key point. Each of these networks can support different maximum packet sizes. This variation is what creates the need for fragmentation. Now, you might wonder, why do we even bother sending large datagrams in the first place? Well, it's because sending larger datagrams is generally more efficient. Since headers aren't repeated for each fragment, this reduces overhead and improves overall performance. But despite that efficiency, it's not always possible to send these big packets without breaking them down. And that's where fragmentation comes into play. It's a necessary process to ensure that data can traverse networks with varying maximum transmission units, or MTUs, without losing any information. So, in summary, fragmentation is essential for maintaining efficient communication across diverse networks, even though it introduces some complexity in the data transmission process. Let's talk about some of the main reasons why fragmentation happens in networks. First, different networks have what's called a maximum transmission unit, or MTU, which is basically the largest packet size they can handle. If a datagram is larger than this limit, it has to be broken into smaller pieces, or fragments, to pass through. Another key point is that the source computer doesn't know the exact route the datagram will take through the network. Because of this, it can't predict the smallest MTU along the path, which often leads to fragmentation when the datagram encounters a smaller MTU somewhere along the way. And then there's the issue of header overhead. Every fragment gets its own header, which is additional data needed for reassembly. If we end up creating too many small fragments, this overhead can waste a lot of bandwidth, reducing overall efficiency. So these factors, different network limits, unknown paths, and header overhead, are the main reasons why fragmentation is sometimes necessary in network communication. They highlight the complexity and the need for strategies to manage data transmission effectively. Now, let's talk about some practical limitations that can affect data transmission. First, hardware and operating system limitations. Some systems have built-in caps on how much data they can send or receive in a single packet. This isn't just a technical detail. It directly influences how efficiently data can be transmitted and received across networks. Next, there's standard compliance. Various national and international network standards specify maximum packet sizes to ensure compatibility and reliability. If a device or network doesn't adhere to these standards, it can lead to issues like dropped packets or communication failures. Finally, protocol differences play a crucial role. Different networks often use different protocols, and each protocol may define its own allowed packet sizes. This means that what works smoothly in one network environment might need adjustments in another. All these factors, hardware limits, standards, and protocols, are interconnected. They highlight how important it is to understand the constraints we face in real-world networking. Recognizing these limitations helps us design more robust and compatible systems. Now, let's talk about the challenges with large packets in a network. One key point is that large packets tend to stay in the network for a longer period of time. This can be problematic because it might delay other packets from moving through, leading to potential congestion or slower overall performance. Another important aspect is error handling. When a large packet gets corrupted, the whole packet needs to be retransmitted. This can be quite inefficient because it means resending a lot of data, even if only a small part was affected. However, if we break down data into smaller fragments, only the specific fragment that experienced an error needs to be resent. This approach reduces the impact of errors and improves transmission efficiency. So overall, smaller fragments help mitigate delays caused by large packets and make error recovery quicker and more efficient, which ties into our broader theme of optimizing network performance.